Okay, ladies and gentlemen, welcome to another meeting of the Columbus Astronomical Society. Got a lot of interesting things coming up here. First, we'll start off with any visitors tonight, new people. Show of hands. Okay, 2, 3. Welcome. So I guess first we'll do the preliminaries. Go ahead.
We have a couple of guests here this evening. Ben and Beth Paulson. And welcome. Anything you'd like to say about yourselves?
On the spot.
Yeah.
Where are we? We also have Dave and Molly Taylor. Maybe they're right behind them.
They're all
Welcome. Yeah, anything that you'd like to say about yourselves, or just that you're...
not really.
Okay.
Trying to learn something.
And what, right, that's what I'm here for.
Well, he's just punched to be here.
Okay. I also have a couple of requests for outreach events that I want to bring your attention to. If you are interested in helping, I have a sign-up sheet here that I'll pass around. They are both on April 19th, which is a Friday. And one is at Freedom Trail Elementary School. And it starts at 12:45, and they want someone to do 3 40-minute sessions, 2 groups of 25 students. And that's going to be at Blue Center. I have it marked on the sheet. The other one is a STEM night from 5:30 to 7:30, and that's at the Westerville Community Center. So I've kind of divided out like that. But if you are interested in helping out with one of those events, I would invite you to sign up and let me know. If you're going to sign up, give me your name and telephone number. Okay? I'll just start around here if you would pass it around.
Thank you. Okay, thanks. Next, I guess we'll hear from Don Stevens. He's our host here at Perkins. He's the director. Have a few words.
Good evening. I'm Don Stevens. I'm the director here at Perkins Observatory. First thing I'll talk about is we do programs, public programs on Friday nights throughout the year. I got a couple more this month that we're doing, and then we're taking a short hiatus for the eclipse. I'll be out of town for a couple weeks, so the programs will be resuming, and I'll have to turn that off for everything. Resuming in mid-April. So, but we're looking for volunteers to help out with things like parking and telescopes. And you don't need to be an expert, all right? Just we need folks out there with telescopes, and they often pair inexperienced folks with those that are more experienced. They can help you learn to find things, and you don't even have to have your own telescope. We have a few telescopes here that can set out there for you to use as well. So just bring your enthusiasm is all we ask, and if you don't want to do telescopes, you can help out with things like the parking. I'll help with that as well. Yes?
Don, if we don't know how to use telescope, would somebody be able to help us?
Yeah, so I said I'll pair folks with someone experienced. That way they can help learn how to point the telescope, how to find things, and stuff like that. So, so if you got something, nothing to do on a Friday night, come out and help out. That'd be appreciated. The other thing is, for new telescope owners, we're offering workshops. This last Thursday was the first one. It was mostly about telescope basics. The next one, next Thursday, is on binoculars and integrated observing with binoculars and solar, lunar observing, what we call advanced observing techniques, things like that. So if you want to learn how to observe the sun, for example, for the upcoming eclipse, that's ideal. Sessions are $50 per person, and if you're interested, give me a call. I'm happy to sign you up for that. I will repeat the series in the fall with the beginner telescope stuff. I just haven't figured out when that is yet. I'm laser focused on the eclipse right now, so I'm not even really thinking about stuff in the summer or fall yet. But I will make an announcement when I get that scheduled. Just reach out to me if you're interested in that. The other thing is, I know the club's selling eclipse glasses, we are as well. And if you hear folks that need eclipse glasses, you can point them to the club, or you can ask them to point them to us as well. And the proceeds go to doing things like painting the ceiling in here, doing some much needed cosmetic work to the observatory, things like that. And eventually, I'd like to have enough to redo the restrooms downstairs and stuff like that. So every penny helps. We're also a not-for-profit. You can make a tax-deductible donation to us as well. You can do that either by dropping the donation box in there, or we have online donations now through the university, and those are tax deductible. So thanks a lot.
Okay, next we got Isaac Cruz. He's our, Cassis, right? And I'll let him respond.
Well, good evening, everyone. My name is Isaac Cruz, C-R-U-Z, and I am the for CASIS, which is the Columbus Astronomical Society Imaging City. So, as the name implies, our group, our little special interest group, actually just goes ahead and tries to help anyone and everyone that is interested in imaging the sky, so taking images of what is up there. We normally just meet here on this wonderful venue on the third Saturday of the month, right? So this is the second one. So next Saturday, we'll actually have a meeting here at 1 o'clock, 1 p.m. In this place right here. And if you have any questions in regards to, how to take images, I'm pretty sure everybody is focused now and actually trying to take images of how to actually do images of the upcoming solar eclipse and so forth. I'm sure there'll be a lot of questions about that. So we'll be talking about that as well. Everybody's invited. Normally I send out an invitation for the membership at large and to the members of CASIS, usually like on Wednesday before. So next week I'll actually be doing that. And again, you're all welcome to come here again next Saturday, 1 p.m. If you're interested on how to image, things in the cosmos. Thank you very much.
Okay, Brad, you got anything to
Sure. You guys probably know me. I'm Brad. I am an astro nerd. I am the director of Perkins Observatory, or not Perkins Observatory. I'm the director of the John Glenn Astronomy Park. Don Stevens is the director of Perkins Observatory. Down in the Hocking Hills State Park. Has anyone not been to the John Glenn Astronomy Park? Okay, so it's in the Hocking Hills State Park, about an hour south from here. Much darker than here, much darker than any place in the suburbs. So if you want to observe the night sky in its pristine glory and the moon is not out, that's important because the moon can actually wreck the night sky. Drive down there, take a look. If you want to observe on a Tuesday night because it's particularly clear and beautiful, you're more than welcome to do so. On Friday and Saturday nights, we have public observing programs. They start always at the same time, sundown. So if you're there at sundown, you'll be a part of the program. If you would like to help out, you can bring a telescope and we would be eternally grateful. That is the help, that is the reward that you get for being down there. Plus it's a beautiful night sky and you get to show people the wonders of the universe as well. It's pretty neat. Next weekend is the backup night for the Columbus Astronomical Society Messier Marathon. A Messier Marathon is a night in March where it is possible, albeit very difficult, to observe all of the objects in the Messier catalog in one long, bleary-eyed night. You start off over in the east, and then you work your way west, and as you get further and further to the west, things rise up, and just before dawn, you get the 110th object, or 109th object, if you don't count M102. You can do that. This is some curious thing that amateur astronomers have been doing for a long time. All of a sudden, I feel really loud. And so if you would like to do this, as a member of the Columbus Astronomical Society, I am hereby inviting you to be a part of this and go down and observe from there. If you don't want to be a part of the crowd, we have 4 acres you can set up in our field out there. I would probably bring a tarp at this time because it's been raining a lot, but our field does drain really well, so if we had at least 1 or 2 non-rainy days before the event, then it should be pretty dry. There's a lot of gaps in the rocks that are under the soil, so it does tend to dry up a lot very quickly. One thing you can't do on site is camp. We have an agreement with the Hocking Hill State Park. Camping has to be done in one of the official designated camping sites. If you would like to actually camp, insofar as setting up a tent or something like that, you can do that in the Old Man's Cave campgrounds. There is a fee. It changes depending on the year. I think it's for tents, it's something like $15 or something like that. You can also, if you'd like to go luxury, rent a cabin. You may be a little late to do that for next week, but there are cabins which are literally walking distance from the John Glenn Astronomical Park. You can actually walk through a little gap in the trees and get to us, so you can do that as well. And while you cannot camp on the site, there is no restriction on you taking a quick little cat nap in your car before you drive home at 5 in the morning, bleary-eyed and about to wreck. So if you want to do that, feel free. If you want to help out, that's great. If you want to just come to one of the observing programs and not help out, we do request that you get a parking permit. On our website, it's jgap.org. And there's usually a link on the first page there to the registration. It's free. That just allows us to know how many people are coming because we have a finite amount of parking. We say that space is infinite, our parking is not. So if you're just going down there to enjoy a view through our big 28-inch telescope, you're more than welcome to just hang out and do that. But please get a parking spot because we do run out of room, and that allows us to know what's going on. Yes, Jason?
Which night is this, Brad?
This is Saturday night. I'm sorry, I might not have said that. Yeah, this is the backup night. Last night was the first night, and obviously we didn't do it last night because it was pouring down rain. So, but it's next Saturday. Yeah, Mark.
Is it possible to show other visitors the night sky and accomplish the Messier Marathon afterwards, or?
I would say that it would be challenging, but you could do that if you would like to explain what you are doing and just set up on the plaza and say, hey, I'm trying to do a Messier Marathon, here's what it is and here's what I'm looking at, and give people views. You're more than welcome to multitask like that. I don't have any objection to it. If you want to kind of steadfastly stick to your Messier Marathon program, if you want.
So if we're going to kind of stick to the Messier program, we should get a parking pass.
No, I think
Or
I've actually held back some of the parking passes for next week, so there should be enough room. You should be good. We will have enough room. I would get there a little bit early so you can set up your equipment and stuff. I mean, if you get there at sundown, there will already be a lot of people there. But if you want to unload your equipment and that kind of thing, it's probably the best to get there a little bit earlier. So it will be. We're springing forward, so it will be 7:30 and not 6:30 next week. So I would get there at 6:30 or something like that. The new daylight savings time version of time, 6:30. Yeah, that would probably be best. But yeah, I did hold back about 20 parking spots for the registration for next week. So, anything else? Okay, I definitely appreciate it. Thank you so much.
Okay.
Charles, one more thing. One, can I say anything?
Yeah.
Okay, good, thank you. One, this is Isaac again, I'm just kidding. Okay, one of the benefits, I forgot to tell you, that one of the benefits that you all have as members of the Columbus Astronomical Society is access to something called Astrospheric. Astrospheric is, weather forecast app. You can actually put it in your telephone, but you have access to it as well if you just go to our website, which is columbusastronomy.org. And on the upper right-hand corner, there's a tab that actually says Astrospheric. And if you click on it, it's a very, very, very good, weather forecast system. One of the neat things is that we actually, because you're all members, we have the benefit of having the pro version being part of your, of the things that you actually see. If you put Astrospheric on your telephone or your iPad or your tablet or whatever, it will be the pro version as well, because it actually is registered on your name. It's just that your name is part of CAS. So there you go. By the way, for next week, the long range forecast actually looks very good for the night of the 16th.
Excellent.
So, that's what one of the things that you can actually look at. Very nice. If you have any other questions, please let me know. I'll be more than happy to let you know. Thank you.
Okay. We have a guest speaker tonight, Sultana Nahar, and from OSU, and we're going to talk about the sun. Okay. So we will begin now. Solar.
Okay. So, hello everyone. This is Sultana Nahar from the Astronomy Department of the Ohio State University. So today I'll be talking about our star, the sun. And this is, there's a special attention at this time because of this possibility of seeing this complete solar eclipse. So Brad mentioned about it, and sun is the object that I've been working for a long time. So it gave me the opportunity to talk about our own sun. All right, and when I was just making this front page, I found, and I looked for something just, we see it every day, and sun is so beautiful, this golden sunshine on the grasses. The picture looks very good, and so I put it here just to tell this is our sun. Every day we see it. Okay. Now, sun is a star, and it is in the space, and we don't bring it to our laboratory to study it. So anything in space that we study is through the radiation or signal we receive, because those photons coming to us carry a lot of information, and that's what we study. So this is just one beautiful picture of the universe. It has 43,000 galaxies. It is an old one. Okay, but it shows beautiful collection and how the universe can be captured, through the light. But each color here, you see, they all represent, it's like mass, velocity, and other properties. They all combine, to form this universe. But it is just a small fraction of total number of galaxies we have. We usually say, there are 2 trillion galaxies we have in your universe. But it is also changing a little bit. But let's assume there are 2 trillion galaxies, and this one has only 43,000. And one of the dot actually is at the center is our own galaxy, Milky Way. Milky Way is a beautiful galaxy in the sense that it is very stable. Most of the galaxies, many galaxies, they have like turbulence going on, stars are forming, a lot of things are unstable. For our Milky Way, it's pretty stable and going smoothly, and it will go for a long time. It has long lifetime. Okay, and one of those, there are about, we say about, in our galaxy, about 200 to 400 billion stars. So we are just one of them. We are not at the center, but we are near the edge somewhere around here. Okay, so it is a safe place. The reason it is safe because we have huge black holes inside, in interior. So we are away safely. Not only that, our sun is also very conservative. It gives out radiation in certain manner. It is not blowing out very easily. It will run for a long time. So we are very lucky to have our own star, which is very, very stable. And also we are not in the center. So in a way, we are lucky to have our own galaxy, also our own star. Now, how do we study? We just say we study, everything through the signals or the radiation we get. If it is a star, it is usually the radiation. If it's say gravitational waves, it's kind of signal. It is not electromagnetic wave, but we catch it and we study it. The close-up picture of the sun is like this. Okay, so it is a very thick, dense, very hot ball of plasma. Plasma means they're all charged particles, and they're always moving. It's a huge one, and when any charged particle is moving, it creates radiation and also creates electromagnetic waves. So it creates also magnetic field. So here, these white spots, they are like magnetic field created by the motion of these plasma particles. Okay, I was told, you know that magnetic, you all know this one, magnet, and it attracts particularly iron. I'll be talking about iron quite a bit because iron is also focused in my study. And you have seen you've seen in your school this magnet and how it attracts this iron, the polarized, and so that the opposite charge come close, and that's how you can close them up. Okay, now our sun has 8 planets and a number of dwarf planets. Pluto is one of them, but of these 8, from this Mercury to the Mars, we have like solid planets, and the rest of these are our gaseous planets. And we are in between somewhere here, very small planet and very small compared to the sun. Like our diameter is 110 times less or smaller than the sun. So sun is giving out a lot of radiation. We just get a small fraction of the radiation, but that is all we need. We need that much energy to survive. Okay, so now let's talk about this eclipse, which is coming on April 8, and OSU has a program at Marion campus. If you want to go there, they will supply those glasses so you can see it. And what is this eclipse? It is some event we like to watch because it is cosmic and it doesn't happen every day. And when it is total, we don't see it usually very commonly. So we get excited or something happening out there. So what is that? So say this is our sun, and say this blue one is our Earth. So when the Earth puts a shadow on the moon, we call it lunar eclipse. If it does it on the sun, or moon does the shadow on the sun, we call it solar eclipse. So when this is our sun and moon is going around it, so when moon is in between, if all of them in the same plane, in general they are not in the same plane, but if they come all in the same plane and the light is blocked by the moon, then there is a point, area where you don't have any light. We call it umbra, and that is where we can get the eclipse, a complete eclipse. But if you move away a little bit, say for example on this side, maybe this side is not reaching there because of the blocking by the moon, but some light from here will reach there. So we can see a partial of the moon, okay, so eclipse. So if there is no, completely blocked by the moon, we have umbra and we don't see the sun at all. Or if you're on this penumbra, then we can see only partial eclipse. But in between, if we are here or go back and forth and move this one closer or something, so some of the light will pass around it and reach us. In that case, we call it antumbra, where we can see this annular kind of eclipse. But on April 8, we are expected to see this one. Okay. So we are interested because it is happening in the space. We like to know what is going on in our sun. But does it have any consequences now for us? Yes. Scientifically, yes. Okay, so the sun is very bright. We don't see everything around sun because it has too much light around it, but it has three thin region outside it. So this is the sun. If we block the sun, then we can see something. Around it you see, this light area is called photosphere. It is connected to the sphere or the surface of the sun. Okay, so and the light from there or photons from there, we see them and we study them a lot. It's called photosphere. But if you go a little bit farther away, it's about 250 miles long. But if you go farther away, we have something called chromosphere. Okay, the temperature from here, is sun's temperature, is about 6,000. So it goes down to 4,000 if you go to the end of this photosphere. But it's strange, if you go to chromosphere, the temperature starts to rise. It goes from 4,000 to 8,000, okay, around somewhere here in the chromosphere. So it is going up. Then suddenly we have this transitional region when suddenly the temperature rises. So there is a jump in temperature. From 8,000, it can go to 500,000. And not only that, if you go farther away, that region, further region is called the corona. If you go farther away, it has increased by million degrees. It is very unusual. If you go farther away from a hot object, how come things are getting heated up? This is a mystery. This was first detected by someone named Edlin at Sweden. He can be called as the father of experimental spectroscopy. He found a line in the solar sphere, solar flare that was in the going in the corona side. So how do you detect when you see photon? You catch it and then you do spectroscopy to find out what is that photon, which element it is coming from at what stage. So it found out it is from iron 13. So iron has 26 electrons. If you just strip off one by one electron, its charge increases. So when it's iron 13, means 12 electrons have been taken out. So that is iron 13 is charged, and it is not very easy to excite, but it was excited. So he matched that line with iron 13. So usually what we do in the lab or study, we find out what should be the energy of a photon coming out from a particular atom or element. And then if we see something, we match it. And that's how we can tell, okay, this photon came from iron 13. And so he did calculate what temperature can make it possible the iron 13 line to be seen, and found out that the temperature was million degrees. So it was a puzzle, and we haven't solved the puzzle yet. It's still a puzzle why it should be so hot if you go away from the sun. Okay, so there are some theories, a bunch of theories. So one of the latest one I'll talk about, it says the sun has, there's something called plasma rain. The sun ejects out materials, the plasma in the space, but instead of going out, it go out and protruded and drop down to the sun. So it's like plasma rain. But it goes up so much that it enters that corona region. So now the discussion is that it is reaching that corona region and it is heating up that corona region by this kind of plasma rain. So this is one hypothesis. But it is a puzzle. Maybe someday someone, particularly younger one, may be able to solve it. All right? So the sun, whenever it is very active, when we say active, that means it has created large amount of magnetic field around it. And when there are a lot of magnetic field, then sun becomes very active. And it has now north and south pole, it flips. South becomes north, north becomes south. When it does flip, and now it is very active and ejects out a huge amount of materials. So these are all charged particles, strong radiation. We can't take those. They will cause cancer immediately. But when they eject out, they go all around. So they also come to the Earth. This is our Earth. But we are lucky. We have shields around us. 3 kinds of shields, probably you know. First one is what? Ozone layer. so it can block the strong radiation. We have air atmosphere, it also deflects a lot of particles. And the third one is what? Invisible magnetic field. Yes, so it can capture, magnetic field captures the charged particles like the way I just showed it. Okay? So that's how we are protected. But when they come and go to the atmosphere, they get burned and create beautiful kind of images. They are called aurora borealis. So you can see it is one of them. There are a lot of them. You can see, common people love to go there and see this borealis. But I just want to show you one picture, the amount of charged particles that reach to our Earth. In 2003, in like end of October, like on Halloween Day, there was a storm. So we call it Halloween storm. That so much particle came to our Earth that they were measured and put in the model. And see, all these particles came to our Earth, but they are all hanging out there, not coming to the surface of the Earth. So we are protected. So this is our Earth, and see this huge amount of materials are coming. So we are lucky having a beautiful Earth and protecting us all the time. So this, now, this was also something, taboo in the past. So because I just wanted to give credit this person, Christian Darkland, because his life came out in the newsletter of APS, American Physical Society. So before him, everyone used to think something ghostly about this thing, you see in space, suddenly so much light, something is there. So he wanted to solve what is that, and he went to all corners of the Earth and tried to find out, what is that. He is the one who spent lifetime find out the reason and explaining that is something natural. Okay, nothing is behind it. Okay. Now, just show about that storm, what we study in the sun. Well, something is happening, so we have to collect information. The more information we have, the more power we have to solve things. Okay, so this shows during that storm on October 28, 2003, you see this white is what? Lot of magnetic field. That means sun is becoming very, very active. After seeing that, then it was observed by SOHO. There was an observatory in space dedicated to study the sun. Okay, so its detector or a spectrometer detected, it is blocking the whole sun, and see the amount of materials are ejected out from the sun. The sun is this much, and that much materials are coming out. After they took the picture, 8 hours, after 8 hours, this detector surface was swarmed by these particles they call proton shower, because they travel 8 minutes, sorry, not 8 hours. Oh, 8 hours? Yes, 8 hours. So they travel and they came to the detector. So this is what we know that the storm can cause. But what is happening, so we should be careful because it also affects our communication system and other stuff. So they are detected, this is like signals, and the wavelength is very small. These are X-rays. So X-rays are small wavelength. So they, the measure of X-rays, so a lot of X-rays were coming out of the sun, and then they were put in the plot, and when you see this plot, you can see the X-rays from this wavelength to that wavelength, and we can see there's a bump. And this is what we do in spectroscopy. What is this bump? This bump is that the X-rays here were created by calcium. X-rays here were created by iron. X-rays here were created by nickel. So this is what we know. So that means they are in the sun and they were emitting a lot of X-rays, and that's what we detected. Okay, but we have a lot of observatories now. I don't know hundreds, maybe it can be thousands, in the space. But it started observatories, particularly the ground observatory started in 1420, and it was started by a sultan, not a typical astronomer. He was very much interested in astronomy. So this is madrasa, Islamic school. So behind this madrasa, he built up an observatory and look at the sky to study, and he himself cataloged over 1,000 new stars. His name was Ulon Beg, and the general people, including his son, thought he has gone crazy, And the record shows that he died of accident outside the observatory. It also says someone threw him out of the window, because thinking he has gone crazy. Okay? So in the past, that's what happened. I just want to show how much we pay attention to the sun, because this is a very special star. Not only sun is the source of our energy, without sun we cannot live. It is also a standard to study other stars. Whatever stars, this is the standard. So whenever we see any star, we want to see, the amount of elements they have, temperature, density, plasma, all kinds of things, but all compared to the sun. So we have to know everything very accurately. If we have uncertainty in our study or the theoretical numbers, that will be extrapolated to the other stars, and we'll get all kinds of numbers which may not be real. So I just showing 4 different dedicated observatories in space to study sun. Some of them are active, some are gone, and one of the observatory is called Parker from NASA. It really went close to the sun and even went through the corona. This is the only one which went through, so it had to withstand very intense heat. Okay, so recently, very recent, also people are observing. There's another space observatory launched by India. So it's called Aditya L1. Aditya means unique, not just one. So the reason I wanted to show you, just to give an idea on how you launch something in space. Okay, so this is showing Aditya how it was launched. So whenever you launch, you don't send something directly, right? It has to go around the Earth in elliptical motion. If it is circular, it's not doing much things, because we are using the gravity to give the push. So if it starts elliptical, it goes, and when it comes toward the Earth, it speeds up. But then because of the speed up, when it is going out, it also speeds up and make a longer loop, okay? And a longer, ultimately, it just goes straight to see this is the object, this is the sun. So it came, and then it went around, and then it set itself in this orbit to observe the sun. And recently, so it is very recent, and these are all pictures of the sun. So observed in the chromosphere and also in the photosphere. So you can see all kinds of sun, images of the sun. Okay, so we know that a lot of study is going on about our sun. But sun is beautiful, we need it, because of the sun, the Earth is very, very beautiful. Because of the sun, we have seasons, because our Earth is a little bit tilt, so we have season, and it is very, very important for us. We cannot live without it. Not only that, the beauty, we don't know anywhere we have this beauty. We can see blue sky during the daytime, but pink sky during sunset and sunrise. The blue sky, because sun gives out all kinds of photons, blue photons, red photons, everything. But because it's direct during the daytime, when it is being scattered by the atmospheric molecules, the blue photons, they are reaching our eyes, the Earth. So we see the blue sky. Okay? And it is also reflected in the ocean, so it looks a beautiful blue ocean. But what happens in the evening or in the morning? So sun is going down, and the sun is here, and we are here, and we have air. Okay, so when light is coming, it has to pass through the air to reach our eyes, so that we can see the sky. So when it is coming through the air, it bends. That's called refraction. So it is bending. It's only the photons which are red, they are reaching the Earth. So that's why when you extrapolate, it looks red. So during sunset and sunrise, we see the sky is red. So they all look beautiful. So we're living, we are happy, but it doesn't mean it is permanent. The sun has lifetime. Each star is born, goes through a lifetime, then it dies. So our sun will also die. maybe in 6 to 7 billion years, but it doesn't matter. We are intelligent with our brain in the head. We have to move on. Our generation, human race should continue, whether sun is there or not there. So what will happen? The sun, right now everything is beautiful, and the source of energy is there because nuclear fusion is going on in the sun. Sun is made largely of hydrogen, and at the core, a temperature is very high, the pressure is very intense, so it's a nuclear fusion can take place. So two hydrogen atoms, they fuse to form a helium atom. And little part of that two hydrogen, when they fuse, but extra part, that mass converts into energy like gamma rays, okay? And that gamma rays start to go out, and we, ultimately, those rays come out and we see them. So as long as the hydrogen supply is there, we'll see the sun the way we've been seeing it. But what will happen when all the hydrogen will be now used up? So that time, everything will collapse. Okay, now all the materials will collapse, but there are a lot of electrons, so negative charge, so there will be a repulsion. So it will just, the whole material, gaseous material, they will expand. So this is our sun today. When it will expand and become a red giant, it will be this big. That means our Earth will be engulfed inside too. So we will be gone too. But we don't want to have that happen. Why we are using our brain? Why can't we use our brain? We have to do that. Okay? So it also means that, okay, so after that, what will happen? After red giant, so it's still, there are a lot of temperature and radiation pressure. The material slowly will be dispersed into the space. When it will go into the space, it will become a planetary nebula. Okay, nebula is just a dying star. At the center, the core is very dense and hot, and the heat is pushing out the materials and illuminating these gaseous medium, and that's how it looks like, something nice. My doctor told me, do you know, they said they have found the eye, God's eye in the space. I said, no, I never heard that. He said, I'll send you the picture. So he sent me this picture. So God is very angry. So I wrote, God is not angry, it's just a dying star. Okay, so what will happen? All the materials are gone. So we have just a core, okay, very hot and dense core. And it will start to, by pressure, this helium, everything will turn into carbon. Like carbon, and diamond is nothing but the carbon. Only structure is crystal is formed. So I like this one because they found in 2014 a diamond white dwarf. See, this is the white dwarf. So we love diamonds because it shines, right? So someday maybe we will be exploring space for diamonds. So can happen. So it's still, but not all of them turn into diamond, but this one did. But what will happen? It will keep on giving radiation until all the radiation is gone. It becomes cold and it will become a black dwarf. But our universe is not old enough to have any black dwarf yet. So we haven't seen any black dwarf yet, but we know it will come. So what is our plan? So we have to find a place to go after the sun will be gone. So we have to find an exoplanet. We have many exoplanets. We have found over 5,500 planets in our galaxy at this time. We are detecting it almost every day. But we don't want any exoplanet. We want something like habitable. It has solid surface we can walk. It is not too close to the host star, so radiation will not bother us, and it should have water and oxygen. So we have been looking for it, and we are very lucky. Our closest star is Alpha Centauri. Even though it is closest, but it is still very far because the light starting from that star takes 4 years to reach the Earth, our sun, right? So we used to think Alpha Centauri is just one star. It turned out it is not. There are two stars, And recently we found it also has a planet. And not only that, it has habitable planet. That means this is our next step probably, stoppage, you can go, With our current technology, it will take 18,000 years. But we cannot do that, right? So a lot of ideas are there. Our brain has to be active, right? So everyone, it doesn't matter how old you are, you can always think. Brain, in whole life, we just use 10 to 15% of our brain. So don't worry that, we have used our brain when I'm old. There are a lot of brains sitting there, you can still use them. So, okay. So you can think about like Newton any time of your life. So there is some idea, First, if you can send something to that exoplanet, that means we have reached there, we will find a way to go there. So there's some idea, it's some actually Russian idea. So he said, we can make a probe and we have to propel it with laser so it can go faster at 1/4 speed of the light. If we can manage that somehow, then it will take 20 years to reach there. So we need to work on that technology. Okay, so now let's see, but whatever we do, still we have to study our sun and we have to know all the information so that we can apply to other places and other stars and get as much correct information as possible. So one part of the sun that I study a lot, that's what I'll talk today. It is not only me, a lot of people also work on this. So this is the sun. I did not tell the three, yes I did, 3 parts inside the sun. The core is right here. Core is where this hydrogen, 2 hydrogen, they are just fused in nuclear fusion and forming helium. So this is the core where the nuclear fusion is going on. The temperature is 15 million degree Kelvin. So only helium can form. Ultimately, the temperature will increase, and that time we maybe will form carbon, nitrogen, oxygen, etc. So the radiation, as I said, part of the mass will convert to radiation, gamma. So the radiation will come out, and then this part we call it radiative zone. In this radiative zone, plasma is very compressed. It's not doing much, it's just compressed. And also the radiation is going through it, and it has not only hydrogen, it has other elements too. So as the radiation is coming out, they get absorbed. All the elements there are atoms, they absorb the radiation. When they absorb, but they cannot hold it. Okay, the nature is such that they have to give out the radiation, whatever they got, but they don't have to give out the whole radiation. So if you got a very energetic photon, it absorbs, then it can give out a photon a little bit less energy. So in that way, maybe that rest of the energy will be used for kinetic energy or something else. So the photon coming out has lost some energy. So then it is traveling, it gets absorbed by another atom, and again it will lose some energy. Ultimately, it will take a long time to keep on traveling. It will get absorbed and emitted and absorbed until it will come to this region. It's outside, it's called convection zone. Here, it is not just compressed. Plasma is moving, boiling. If you look at the NASA pictures or the surface of the sun, your hair will stand out. The way plasma is boiling. So I'm glad that we are far away. So this is the convection zone. So that's where it will then come, and after that, passing it, then they will escape into the space. And by the time they escape, they have become from gamma rays, slow down, X-ray, visible photons, maybe infrared, less energetic photons. So with those, we detect and we study. Okay. So what is in this inner region? These properties in this region that photons are coming out, they get absorbed and emitted. This is a phenomenon called opacity, like radiation absorption by the medium. The opacity is a fundamental quantity for plasmas, and it has to be calculated because many quantities that we calculate depends on that quantity, opacity, how radiation being absorbed, how much is coming out. There's a symbol we use, kappa. Kappa is used many quantities, and how many elements, we have abundances, various stuff. Okay, I'll show some examples. So what I've been involved, calculating opacity, particularly here, in this at the boundary between the radiative zone and the convection zone. Why particularly at the boundary? There's a reason for it. Okay, this boundary, the phase is different. Here, there's no moving, it's just compressed plasma. Here, plasma is moving. There's a phase difference, the different phase. The sun also oscillates. It has many modes of oscillation because of it. Creates electromagnetic waves and it explodes everything. So from this oscillation, we call it helioseismology. We can determine this boundary, okay, where the boundary lies. So if I calculate atomic number, photon absorption, photon emission, everything correctly, and try to put that to calculate the opacity, I can predict where this boundary should be. So it gives, if I can predict that it is close to what the observation is, that means my theoretical numbers are good, accurate enough, but they are not accurate at this time. So there are a lot of problems. So this has been a long-standing problem. Okay, so I'll show what is this opacity, quantity, and how it is related to the distance. So think this is a section inside the sun, and the radiation, the photons are coming and passing through this section of plasma. So they are entering with one intensity, I0, but when they are coming out, it is I, because part of the radiation has been lost or absorbed by the plasma here. So the ratio of the two, incoming and outgoing, this depends on something called exponential, and inside there is a symbol is called tau. A tau depends on three quantities. This the distance x, the density of the plasma, and there is something symbol kappa. That is what opacity is. That means we want to calculate that so that it can be used to determine this distance. So we can also calculate the distance or the boundary between the radiative zone and the convection zone. Since you are here with me, you have to be part of me too. But you have to learn a little bit atomic astrophysics that I do. Okay. So, all right. So what we are focusing on that boundary. At that boundary, it is not only hydrogen, oxygen there. Even iron is there. Okay. So, but we choose iron to calculate the iron opacity. That means how much radiation is absorbed by iron. Okay. In that particular region, it's very hot and dense. So there's a way we can calculate which ionization stage. Like when I say ionization stage, means are all the 26 electrons of the iron there, or they are stripped off. So the more stripped off, they are called ionization stages. We have to know which ones exist at that temperature, and we found that there are three main ones. The red one particularly inside the sun, and they are iron 16, 17, and 18. Sorry, 17, 18, and 19. You don't have to remember it. Just remember that this number is related to a number of electrons in the iron ions. So we focus on these three ions and try to get the opacity of iron inside that. So you say why you should choose iron, because there are other elements too. But iron acts like a valve. See, iron has many electrons. The more electrons you have, the more ways the photon can be absorbed in a particular energy region. That means it can absorb more photons than, say, oxygen. Oxygen is also there, but iron is absorbing the most. So it's a valve, how much radiation should pass through that region. So that's why we focused on iron. So now we need to do a little bit in atomic physics. Not atomic, we're not doing much, just the general idea, okay? You are amateur astronomers, so you have that base, I know. Okay, so this is the atom, and we have electrons. And electrons, when they go around the nucleus, it is not a random orbit. The orbit is fixed. If it is going the orbit, it cannot be just here. There will be in a quantum state. So it will be maybe a state here. So it can be either here or there like that. Okay. So the particular orbit they can go. So that's why we call quantized orbitals. And because they are quantized, we know their energies. Okay. So we can write or draw their energies. Say when everything is in the ground state, minimum energy state, this is the first one. But if the electron moves up, maybe the energy will be that much. If it moves some more up, this is higher and higher energies. There will be no electron in between, but they are all particular energy levels. So what is the advantage? This is the nature, what is helping us to do the spectroscopy. Because they are fixed, we know the fixed energy difference. And this difference is unique for each ion and atom. So if we capture one photon, we can always compare which atom, one photon we compare with any atom, and you can say, oh, this came from neon, because they have fixed energy differences, fixed, particular kind of photons can come out. So that is the advantage of this nature, quantized. But there are infinite number of energy levels. So the infinite number of photons can come out. Okay, but some photons, you can come in this energy region. You can have a lot more photons. Sometimes you can have small number of photons. Depends on these energy levels. So what we do, that is what we study, and that is so-called spectroscopy. What spectroscopy means? When you have a bunch of photons, you separate them out. Say red photons, blue photons. That is a spectroscopy. Like a rainbow. Rainbow is the spectrum of the sun. Okay. So if we let the photons go through a slit, so they come out as a lines like that, and it is easier to study. But if it is go through some medium like prism, so it is come out, they can be continuous, all the colors are showing up. Okay, so this is called a spectrum. So this to show that we always match. For example, this spectrum is for carbon. So whenever we see a spectrum from any astronomical object, we see line, say JWST. We match this line with one of them. And if we see, oh, it matches with this energy, say, oh, it has carbon. That star has carbon there. Okay? All right. So, but these kind of things, we are not doing it just now. We have been doing it for a long time. So Fraunhofer, 200 years ago, 1815, he was also watching the sunlight coming to Earth, and he did some spectroscopy, and he saw a bunch of lines like that. But he didn't know what are these. Okay? So what he did, he just from the sun we can see some kind of lines. So he said A, B, C, D like that. But we didn't know what are those things. He had to wait for 100 years. Well, he died, but we had to wait for 100 years. Sorry. Okay. So 100 years, because quantum mechanics came after 100 years. Quantum mechanics explain what these lines are. Quantum mechanics say these lines belong to hydrogen, oxygen, sodium, those, okay? They match, and they say this. So that's why quantum mechanics is important. But without that, we will not know what kind of lines or photons or the elements the sun has. All right. Not only that, so we can get now theoretically you can predict this spectrum. So you see, this is the spectrum. It is a lifetime work of a person born in Ohio but lived all his life in Harvard. His name is Robert Kuruz. Okay. So this is his masterpiece. This is the thing. So from the sun, all the light coming. So he did theoretically all these lines. That means excitation. All this they are coming to the Earth. So he predicted these lines can be seen. Okay, so more lines, that means more photons are being absorbed in our atmosphere. So if you go through this line, at one point you see there are not many lines. That means those photons are not being absorbed in our atmosphere. This is yellow region. So the yellow region, that means the photons, yellow photons coming from the sun to our Earth are not being absorbed. So that's why we see the sun as yellow. Okay, so that's the advantage. Okay, now we had some fun with the spectroscopy. Now let's go back to our opacity. So opacity, okay, so this is, I love this picture because it is, I saw at NASA I saw, the movie, the continuous movie, this boiling plasma, it was impressive and awesome. Even though I would not like to go there, but watching that, it seems very beautiful and awesome. So I like to use this picture time to time. Okay, now we come to atomic physics again. So these photons, so opacity, we just know that means absorption of radiation by the medium or the elements in the medium. So there are two ways. There are two main ways these photons are being absorbed. Please just remember it. It is not very difficult to understand. There are two ways. So say this is the energy level of an atom. It absorbs a photon and goes to an excited level here. Okay, so we call it photoabsorption. Okay, and if in atomic physics, what we do, if this thing happen, we calculate certain parameters. We represent the atomic system mathematically, and then we calculate some parameters. You don't need to worry about this. These are the parameters we calculate. We use those parameters to get the opacity due to photoabsorption. Okay, so this is one way. So it means that when you do that, we have to do accurate calculation so that the opacity will be accurate. The second main method for photoabsorption is called photoionization. Okay, what happens? See, atom is here. Again, photon is traveling, and when this electron absorbs it, it can go to excited state. It is not. This photon has more energy, so the electron is happy. If it frees itself from the ion and it goes away, so you ionize. So it is called photoionization. So these are the two main way photons are being absorbed by the elements or the atoms inside the sun. So this is the two processes I've been studying for a long time, but seems very simple. Only thing is that when you have so many mathematical things and it becomes big Hamiltonian matrix, you can't do things by hand, so you use supercomputer, then you face a lot of numerical problems, then you don't have enough time. All kinds of things come, but it takes time, but it can be done. So that's what I did. All right. So it is not only me I've been part of a project called two projects called Opacity Project and the Iron Project. Both projects are international, and countries, number of countries involved. Did I list the countries? Not, maybe not. So the first our leader was Mike Seaton and at UCL, University College London. Okay. So, and the first, there was so much study we did, we had to develop codes, then run things, and difficulties finding the right computers. The first publications, it's not showing, it's the first volume of publication. It's just one. There are many papers have been published after that. And people involved, right now I think listed 52 members. There are some more you have to add, That many people have been involved to calculate accurate atomic parameters, to calculate opacity, and not only that, use them to solve long-standing problems. Okay, so what he guided us to study all these elements in the periodical chart which are astronomically abundant. Can someone say which are the most abundant element? Hydrogen and? Yes. So first hydrogen, you can see here that as a hydrogen, helium, and then you are right, carbon, oxygen, they go, and then there is a jump again in iron. So beyond that, all are a small amount, but when the project started, the computer power was not that great, so we had to limit ourselves how much we could do, and so we just focused on all elements until iron, only this. But these elements also form in the stars, or during supernova explosion, or during this they call kilonova, when merging two black holes. But those are not now for opacity project. So, but this opacity project ran for a long time, and under this study, new things came out, new physics came out. Not only new physics and new application, even 4 databases were built, okay, top-base, tip-base, OP server, and one is at Ohio State University, NORAD Atomic Data, which I maintain. Okay, and solve problems. Many problems are solved. So I'll just show 2 examples. So one is that the sun, we say sun is a black body. The reason is that it has constant temperature on the average, like 5,770 or sometimes say 6,000, whatever is constant. If it is now something is that hot, it gives out a radiation, and that radiation follows one particular characteristics. Okay, I'm not going to get it, so it is okay. No. All right. Yes. Okay. So this is called Planck's law. So when we measure the radiation flux coming out from the sun, they match this this Planck's law, except in this region they are not matching. They are like observations. Here, the flux coming out more than expected. Here, flux is coming out less than expected. So I'll explain less than expected, because this is something I did. So it is like iron. So where I studied the opacity, this shows the opacity of only one particular ionization stage of iron 2. So you can see that here the wavelength is here, like it's 2,000 and 3,000, something like that. And if you see, the most of these opacity means more absorption here, less absorption here, because you can see the peak. And this wavelength is again matches that. That means on the surface of the sun, iron 2 is there, absorbing the photons. It's not, they are not letting the flux come out. That's why it is less. Then the question comes, do you believe that the iron should be on the surface of the sun? Iron is heavier than other elements, hydrogen, helium, right? How come it is not sinking but floating up there? So there is a reason for it. Okay, so gravity is pulling it down, but there's another force. It's called radiation force. So much radiation coming out from the sun is pushing, the elements to go to the surface. So when they are equal, the 2 forces, then they start to float. So iron 2 has been floating, so absorbing. So this is one success. The other success is now something called Cepheid variables. It's one kind of star which goes through a pulsation. That means it becomes brighter and then dimmer. It goes through a cycle. But that cycle is again related to the opacity of the elements inside it. Okay, what this cycle though, so astronomers could not match the prediction with the observation. So see, this is like this pulsation rate. You don't have to understand all of those, but it is related to the pulsation rate, and these are the observations they have been seeing, and the atomic data or the opacity they are using, that's what they are getting. No match. So they are the ones who first called in early 80s, can you do some accurate atomic calculations so that we can have accurate opacity so we can see whether we can match the observation with the theoretical prediction? And that's how the opacity project started. And at the end, it was successful to explain this observation by reducing the discrepancy of observation and the theoretical prediction. See here, so that's the final results. So I just showed 2 examples that opacity project did or successful, but it was not successful in explaining our sun. So our sun is, if I show the sun, say this is the sun, and the 1 means surface. The temperature curve goes like that, very high temperature, 15 million degrees go up to this, and that's the density. And this is where that boundary is, radiative zone and the convection zone, this boundary. So this boundary, I said, has been measured very accurately by helioseismology. And that boundary is at a distance 0.713 and a plus minus this. So this is what it is. But if we use the current opacity and the atomic data, this boundary comes out to be 0.728. So it looks like they are not too far apart. But given the size of the sun, this small difference translates into 5,600 miles. That means this boundary should be somewhere around here. That means we are predicting a sun which is much larger than what we see. So that means we are not doing a good job. Our data are not very accurate. Even though we spend a lot of time doing and developing things, but it's still not accurate enough for the sun. Okay, so then experimentalists join. So at Sandia National Lab, so there's a setup called a Z-pinch machine. So what they try to do, they try to create a tiny bit of plasma exactly like inside the sun in the laboratory. So how do you do that? So see, this is a big setup, and you send about 27 million amp current through it, and at the center there is a gold foil, and when the current goes through it, it explodes. But again, as I have the magnetic, magnet here, so when the current goes through this setup, it also creates very strong magnetic field. It implodes the whole plasma. So the plasma remains there. And what is it? At the same time, we have iron, which just vaporized, a thin film of iron, so it vaporized, and the plasma, the X-ray goes through this, plasma vapor, and then they measure the opacity or the radiation absorption. So that's what they did. When they did it, it became big news. Okay, they said that there was. So we are also part of it. They said they created the sun on the earth. So there are many articles like that. So we become part of this, but our prediction was not good enough with the experiment. Letter. And what that is found, they see the black curve, that is the opacity that was measured. And the blue one, that's the opacity that predicted with our results. So that means there is a big difference. So we did not do the good job. In 2015, that's what we found out. Okay? So we went back to the table. Okay, in that table, so I would like to say that I do a lot of iron work. I have been doing it. Probably in our project whole team, I have studied more iron ions than anyone else. Okay, so I think sometimes I'm called the Iron Lady of Astronomy. They gave me that name. Okay, now what? So we've been working on these iron ions for a long time, and what we just finished. One thing we found, found that what we did had a lot of missing physics in the past. Okay, so this is what I'll just show. This is the sun. This is one iron ion which is abundant inside in that region. Okay, inside the sun. So the red curve, you see the red. These are, you can think that they are all photon absorption or radiation absorption. So the higher it is, the more absorption of photons. So this is what I got after calculating this. But to do that, we had to introduce new physics, new way to do things. Okay, so this is what I got. And what went in the past is this is what, you can see that flat line blue one. That means it is showing no photon is being absorbed, very low. So that's why the past opacity was very low compared to it should be. So this is what we have completed of the 3 ions. So our group, we have written out 4 papers after a long time. So all the atomic physics is in place. And we did, when you have plasma around it, you have to take into account what plasma is doing to these lines. Okay, so my colleague, did that part. So altogether we have, it is under review, the 4 papers in a series. So this is what is this? So this is our big achievement, at least an accomplishment after a long time. Then after that we will work on opacity, not also other ions. So my last slide is here. So this is some preliminary results using what I have got given to my colleague, and he used it. So this is that kind of, I showed an example of photon absorption, but if we start to put plasma in, around it, so it start to change. When you go to the status of the, inside the sun, it has become flat. But when you integrate to get the opacity, it becomes higher than we got before. That means our trend is good. This is our next step. Okay? So that is all I wanted to say today. So, thank you.
Okay, so we learned a little bit about iron today.
Good.
Yes. Ah,
Very important.
yes, yeah. Depends on the sun for sure. So, once again, I'll say, Jim's got glasses, solar eclipse glasses with him tonight. So if anybody is looking for some, you can see Jim here at the end of the meeting. For questions?
Yeah, I have a question. The iron that you're talking about, that iron isn't produced in the sun. That's the iron from the original dust cloud that the sun was made out of, right?
You are very much right, because our sun core is not hot and dense enough to make iron. So when when supernova explosion happens, everything is scattered in space, and then a new star is formed. So our sun formed from scattered materials, and iron was already there. Not only iron, it had gold too.
Yeah.
So we got gold and other materials too. Yes.
Okay, that's what I thought.
Yes. It is not created on Earth. Yes.
So what is the heaviest thing that the sun is capable of making?
At this time, only helium.
What's
But,
that?
at this time, only helium largely, but it also can create heavier elements. If you want to have heavier, you have to have more temperature and more
No,
density.
I mean, we got hydrogen.
Yes.
Using to make helium. How far up the ladder does it go?
Oh,
Because
it
I
will
thought
ultimately.
the iron was the heaviest thing the sun.
Yes,
could
usually up to iron. When you do nuclear fusion, we go up to iron only because iron has the strongest nuclear force,
Okay.
and you stop there.
Okay.
For other elements, it's different. You have to do something called arc process. With arc process, we form those heavy elements. But with the nuclear fusion, yes, iron, it stops at iron.
Are you using iron as a proxy for all of the other elements in the sun to figure out the opacity? I mean, obviously iron is more common, but is it just because it happens to be a particularly common element? A particularly common element in the sun, and it has a lot of electrons that can be stripped away and give you a lot of these interesting ionization states.
You got the right answer, and the question is also very important.
Yeah.
That iron, see, we have more oxygen than iron in that region,
Yeah.
but oxygen cannot absorb many photons. So if you want to calculate opacity, we want to have that element which can absorb the most. Otherwise, it is so much inside, and all we can do is just predict and see whether something big can be seen. So even though iron, oxygen is there, it's not making or contributing a lot toward the opacity radiation.
And given that you're dealing with ionization, and the sun is a big ball of electromagnetic plasma, is the Zeeman effect a factor in that? I mean, are you getting the splitting of the spectral lines and that kind of thing?
Yes. Those are usually, you are right. These things now have to be taken into account when you do particularly spectroscopy. But here, I have taken those into account.
Okay.
And that makes the problem even bigger.
Yeah.
Because you are splitting everything, and the series, there are series of lines they form. So you have more series, and you have to calculate more series, yeah.
Yeah, because you did,
But
I
that
didn't
is
see you
makes
touch
the
on that.
accuracy higher.
Yeah, okay, so it makes it.
So a photon from the core takes years to get to the surface.
Yes.
I don't recall the exact amount of time.
Well, it says 1 to 5 million years, because
Yeah.
it just
Huge
stops so
amount.
many times.
Right.
This approximate time. Yes.
So the sun, and I always get this backwards, it's a population 2 type star, right? It's metal rich, so it's got things that are heavier than helium. And I forget, population 1 stars that have less metal, or is it population 3? I forget. I always get it backwards.
It's actually the opposite. Sun's population 1.
Run, okay,
Population 2 have less.
yeah, and then
3.
population 3 is, yeah. My question is, so because the sun is a population 1 star, it's got these heavier metals in it. In population 2 stars, is the inside of the star different, like that transition area? Is it different because you don't have that opacity, you don't have that, those heavier elements in there?
Well, we don't calculate, opacity of those metal core. They call metal core stars.
Right.
Yeah. But the sun is important. The other ones are so far away, we cannot test and see everything.
Right. I just didn't know if anybody was
But
thinking
for
about
those, we do a lot of spectroscopy and abundance element, and to understand the chemical evolutions and physical conditions, so those diagnostics.
Okay.
Okay, so, any questions about anything else?
So yeah. So, Gretchen, I'm very happy to see you.
Sultana, we danced together. Yes, dear.
Yeah, so we know each other a very long time.
Yeah.
Her child was born in the folk dance. My son was born in the folk dance.
So you guys dance like the photons going through.
That's it.
Okay, well, I guess that's about it for tonight then, except for anybody who wants to get glasses or